Hello everyone. In today's lecture, we'll be looking at the governing equations for fluid flow. I'll start by writing down the equations of motion that govern an incompressible Newtonian fluid. That's an assumption that we'll make throughout the course, that all fluids are incompressible and Newtonian. I will also assume that you already are familiar with these equations, so I'll not be deriving the equations, but rather I will focus on the more difficult aspect, which is determining the boundary conditions at an interface between the two fluids. But let me just start by writing down the governing equations for an incompressible Newtonian fluid. I'll write this first in the vector notation and then I'll switch to the index notation. I'm assuming that all of you are have some familiarity with index notation. There are several excellent textbooks which describe index notation. So let's write down the mass and momentum balance for a fluid. These are problems without an interface. So typically you could have a problem in a container like this. Okay, and this could be two-dimensional or three-dimensional, and we write down the mass and momentum balance. So let's start by writing down the continuity equation. That's the mass balance equation, and the momentum balance equation would be density times the total derivative or the substantial derivative, the pressure gradient term, plus the viscous term. Now you could in principle have other forces at play. For example, if this is a heat transfer problem, then you will have an additional body force term because of changes in density because of temperature, and you'll also have a temperature equation. But we are ignoring all those complexities in this course. And if I were to write down these equations in index notation, so I will recognize that the velocity vector u has three components, three scalar components, where E1, E2, E3 are unit vectors in the 1, 2, and 3 directions respectively. So therefore, the continuity equation becomes, this becomes del ui by del xi equal to 0. Here, I is the free index. Where does I come from? So if I write down the velocity vector like this, u1 e1 plus u2 e2 plus u3 e3, this can also be written as summation ui ei or simply ui ei. So I is the free index, and if I write down the momentum equation, becomes density times del ui by del t plus uj del ui by del xj is minus del p by del xi plus mu del square ui by del xj square. Here j is the free index, j is the repeating index, sorry. I is the free index. This term that you see here, this is du bar by dt, which is del u by del t plus u dot of grad u. Now j is the repeating index, so which means that if j appears in a term, it will appear twice. whereas I appears only once in an equation. So this is clearly a vector equation. Now, what would happen to a problem with interfacial flows? Okay, so let me just write down. In an interfacial flow, let's consider a simple example of a system uh, um, which has two fluids, air and water. So this is an interface. On one side you have, let's say, water. On the other side you have air. Now, air and water, there's nothing special about air and water. It could be any two immiscible fluids, and there is a surface which separates the two. Now, in each of these fluids, the assumption is that whenever I have two fluids, each of the fluids are governed by incompressible Newtonian. So, for example, for the case of air, I have del dot U of air is 0. So the subscript A shows that it's air. And whereas momentum equation becomes d by dt of U air, pressure in the air, viscosity of the air, and the viscous term in the air. Similarly, for water, I have the same equations, but now with the subscript W to indicate it's water. The pressure gradient term in the water, plus I have a viscous term in water. So the motion of water and the motion of air are obviously coupled to each other. You should also write down the continuity equation in water. The motion of water and air are obviously coupled to each other. How are they coupled? They are coupled through the interface. Through the evolution of the interface. So how this problem would differ from a problem in conventional fluid mechanics is that if I were to look at a conventional fluid mechanics where the shape of the boundary is known, boundary shape is known or prescribed to you, you may have to determine, so all of them are basically fixed boundaries, you may have to determine the fluid flow subject to some forces. So you're not trying to determine the shape of the boundary itself. So in a problem like this, if let's say the upper fluid is moving, upper boundary is moving, let's say it could be a lid driven cavity problem, then you will say on each of the boundaries, you would have the velocity 0, or rather you have the components of velocity as 0, because of no slip and no penetration condition. That is true of all the boundaries. This is the kind of typical problem that one would solve where the boundaries are prescribed. Of course, this is not the only example. There are several other examples. It could be flow over an object. It could be flow over a flat plate and a boundary layer flow, and so on. But you're not trying to determine the shape of the boundary. But when it comes to an interfacial flow, you have to determine the shape of the boundary as well as part of the solution. So to determine the velocity field in the air, we need to apply some boundary condition at the interface from the top. Similarly, to determine the velocity field in water, we need to apply some boundary condition from the bottom. I'm using the words bottom and top without any special emphasis here. It could be the other way around as well. Now, how do I go about deriving the boundary conditions at an interface? Now to do this, we will move away from these writing those in the equations in this differential form, but we'll write them down in an integral form. Let's start by looking at the boundary conditions at an interface without considering any additional forces such as surface tension. So we'll be looking at the integral form. Let's start with the integral form. Of the continuity equation. Now, the problem of interest to us, let's say, is enclosed. We are interested in a region. It's an arbitrary region in space. Let's call this region as an arbitrary region in space. And on this arbitrary region, I have a bunch of vectors that are of interest to me. For example, this arbitrary region could be enclosed by a boundary where at every point on the boundary, I have a normal vector. If it's a unit vector, I will put a little hat on top of it. And because it's a vector, I have an index I. The boundary itself could be moving subject to some forces. Let us say the boundary has a velocity of Wi. So we can clearly have a velocity which is along the boundary and a velocity tangential to the boundary. Okay. So let's start with this region. Consider an arbitrary region in space. With an arbitrary shape. Velocity Wi at its boundary. Now we'll start with the Leibniz rule of differentiation. What we have is the derivative, time derivative over an arbitrary region of any quantity f, this volume integral dv, would be the local changes in time at every point integrated over the whole volume plus the variations at the boundary. Again, notice that I is a repeated index. I've just written f without any index, so I'm referring it to a scalar. Okay. So what it's saying is the total change of any quantity inside, the total change of quantity of this quantity f inside the boundary is related to local changes at a given point integrated over the whole volume plus changes that happen over the boundary. So it becomes easy if we assign a physical meaning to f. So let's consider the case where if f is equal to density rho, then we have d by dt of rho dv over the entire region all I've done is just substituted wherever there's f, I've substituted density. Okay. But we will use, so the mass balance equation, Here I've written down this term where the density is actually varying in time everywhere in space. So this is right now not an incompressible system. And therefore, the density equation is governed by the following equation for mass balance. Again, let me reiterate, I'm expecting that all of you are familiar with these equations in some form. And I'm applying these equations to derive the boundary conditions at a moving interface or a moving boundary. Okay. So if I substitute this, what I have is now from the mass balance equation, I have the time derivative, partial derivative of density with respect to time. I can just substitute it here. So what do I have is and to be consistent, if I write everything in index notation, this is dV. And if I use Gauss divergence theorem, I can convert this volume integral into a surface integral. So I have used the divergence theorem here, and therefore I have a relationship between the total derivative of quantity on the left hand side is equal to what's happening at the boundaries. So we can physically interpret this as follows. The left hand side here is the rate of change of mass, and this quantity gives us the integral mass flow rate through the boundary and relative to it. Okay, so I could have a boundary. Let's consider a case where I have a boundary. A part of the boundary is shown here. Now this boundary itself is moving with a velocity at various locations with a velocity of Wi. And further, there could be some velocity passing through the boundary. This is velocity Ui. Okay. So the right hand side basically tells you the mass flow rate through the boundary and relative to it. And the left hand side is the rate of change of mass. For example, if you take a droplet which is just oscillating, let's start with a circular droplet. And if it's oscillating, let's say start with a spherical droplet in 2D. If I draw it as a circle, and let's say it becomes a spheroid. whatever mass is there in the inside the droplet will, if I say that it is not going out anywhere, let's say through evaporation or through some other mechanism, then the total mass inside the droplet is always contained inside the droplet. So if the droplet, let's say, is wobbling or oscillating in this fashion, then clearly the shape of the boundary is evolving. In this case, the boundary has actually evolved. As shown with the blue vectors. And because the boundary has evolved, mass simultaneously has also traveled from the bulges on the outside to the bulges on the upper half. So the fluid has to travel so that whatever mass is contained inside the boundary remains inside the boundary. In this particular case, the total rate of change of mass is 0, left hand side is 0, and on the right hand side ui minus wi at the boundary is also 0. Therefore, the equation is identically satisfied. Now let's consider another situation where there could actually be a mass transfer across the boundary. This is not a fluid flow system. I mean, this is not interfacial system, but it's still a useful example to look at. Let us say you blow a balloon. This is the mouth of the balloon. Okay, and I'm interested in a control volume. The arbitrary region is basically I have a control volume which is basically enclosing this balloon. If I were to blow air into this balloon, then the only way, there are two possibilities if I blow air into the balloon. Either the density has to increase if the boundary is not changing. Okay, that is represented by the left hand side, right? The density is increasing, but the boundary is not moving. If the boundary is not moving, everywhere else Wi will be 0 except here I have a velocity ui. So the right hand side, there's only one term on the one boundary. So there are two boundaries here. There is a curved boundary 1 and there is a mouth which is a flat boundary 2. So left hand side, the equation essentially becomes d by dt over the entire arbitrary region. This is a volume integral of density times rho dv. This quantity will be equal to the changes over the boundary, that is boundary 1, that will be ni rho wi minus ui ds plus the changes over boundary 2 ds. Clearly, the boundary 1 is, if the boundary 1 is not moving, okay, this is a general equation. If balloon boundary is not changing, if for those of you who may find it hard to believe that a balloon boundary cannot change, imagine a car tire. Once you have basically blown air into the car tire and it has reached a certain pressure, the boundary of the car tire does not really change much. But what does happen is that the pressure builds up. The pressure builds up because the density of the air also builds up. Okay, so the left hand side clearly is non-zero. Okay, if the balloon boundary is not changing. Okay, then in this entire situation, what I have is the rate of change of density or the rate of change of mass, because clearly you're pumping in mass into the system. The first term is 0 because everywhere else the boundary 1 is not changing. And for the second term, all that you have is you have ni rho. This is non-zero, but since you're pumping in fluid into the boundary, that will be minus of plus minus u inlet ds, and this will be ni rho u inlet ds, where in this case the reason you have ni and u inlet are of opposite sign here is because I have considered the ni is basically the normal to the boundary 2, and u inlet is opposite to the normal. The normal vector is normally pointing outwards, the velocity u inlet is inwards. Therefore, that's the change. That's the reason for I changing the sign. Okay, so this equation is consistent. Now another possibility which I would like you to think about and work it out yourself is that the boundary 1 is actually expanding. Okay, and the net there is, so when you pump in air into the balloon, and let's say consider a situation where the density is not really changing. Okay, if the density is not really changing, the left hand side, the density is constant, it comes out, but the volume is changing with time, so the balloon is becoming bigger, so left hand side is non-zero. Correct? Now in the first case, again, if you look at the integral 1, the boundary is increasing, that is ui is increasing. Ui is the boundary at the velocity at the boundary, and wi is the velocity of the boundary itself. Again, this term is 0, but the second term is again non-zero because the second term is the inlet to the balloon, and typically that's the inlet that you put it in your mouth and blow air into the balloon. So wi is again 0, but ui is opposite to ni. So in the second scenario, you can actually have a boundary which is varying. Okay, and this equation, the equation that I've highlighted in box, relates the rate of change of mass to what's happening at the boundary, meaning it takes care of mass flow rate through the boundary and relative to it. Now let's write down the same equation with the integral form of the momentum equation. Now we'll again use the same Leibniz rule. Just to recap what we have written, Leibniz rule here is we have written down the Leibniz rule. Let me highlight it with a box here. This is my Leibniz rule. Now what I'm going to do is replace f with a vector now, because we are interested in momentum. So if the variable f is density times the velocity ui, that's my left hand side. That will the left hand side indicates the total change of momentum in the entire volume would be the local changes in momentum integrated over the whole volume. AR represents arbitrary region, plus the changes to the momentum across the boundary. But notice that the index I is already used. It's a free index. So I cannot use I again. So I'm going to use another index. I'll use index J for a repeated index. That is, this is Nj Wj F times ds, where F is rho ui. This is the arbitrary region. Okay. Now this term here, it can be obtained from the momentum equation. What is our momentum equation? The momentum equation is del by del t of rho ui plus del by del xj of rho ui uj. This is valid for both a compressible and an incompressible fluid. In an incompressible fluid, density would be constant. There is some body force Fi. This is Fi is basically body force per unit mass. And sigma ij is the stress tensor. Okay, so we have divergence of the stress on the right hand side. Okay, so from this equation we get, so I should write something like, using this equation we have changes to momentum, local changes to momentum in time. I take all the other terms to the right hand side. And if I substitute this into my original equation, what I have is I have all these terms here. I have these three terms: convective derivative, body force, and the gradient of the stress. This is the volume integral plus what's happening to momentum at the boundary. It will be momentum flux at the boundary. Now we can separate them into separate integrals. So we have the body force term. I can use divergence theorem here. So to replace so first is the body force term here. The next is the convective term. Then I have again I've used the divergence theorem. And then momentum flux at the boundary. Okay, so now I can combine all of them and come up with a single equation. The body force term, which is a volume integral. I can combine the second and the third terms on the right hand side. Second and the fourth term on the right hand side, sorry. So that is rho nj wj minus uj times ui ds, and finally I have the stress tensor term. Notice again that j is the repeated index, so wherever j appears it has to appear exactly twice. Okay, so for example in the second term it is wj minus uj is a vector. Okay, and this vector is multiplied by nj, dot product with nj. So this would be something like n dot w minus u. That's the kind of term that we have here. Okay, and this is n dot sigma. Okay, that's the kind of term that we have here. So this is an important result. Basically, let's put this in a box. This is the integral form of the continuity equation, of the momentum equation. So let's look at the integral form of the mass momentum equation, that's mass equation, which is this equation, or the integral form of the continuity equation. And then we also have the integral form of the momentum equation. Okay. Now, if it were solid surfaces, I will quickly write down the boundary condition in the solid surfaces. These are typical boundaries, but these are not the only boundaries that one would normally encounter in common boundary conditions that normally encounters are the no slip condition. And no slip condition would mean that if you have a boundary, then the tangential velocity along the boundary is 0. Therefore, you would say u dot t is 0, where t is the tangent to a solid boundary. And you could also have a no penetration condition. This should not be true for many porous flow over porous media, where you could actually have a flow through the boundary. But if you have a no penetration condition, then the normal component of the velocity at the boundary would be 0. Okay. Now, to even apply these boundary conditions, you need to know where the boundary is, right? Now, the next step would be to determine what are the boundary conditions at an interface which is evolving in time. So that's something that we will be looking at in the next lecture. So just to quickly summarize, what we have done in this lecture is we've written down the integral form of the mass balance equation or the continuity equation and the integral form of the momentum equation. Now we will use these integral form of these equations to construct the mass balance, the fluid flow, basically mass and momentum balance across a boundary in a thin volume, and then we'll shrink the volume to a surface, and that's how we will get the jump conditions or the boundary conditions at an interface. That's something that we'll be looking at in the next lecture.